weapons, and lots of new synthetic elements were discovered, particularly plutonium, which had never been discovered before. And after the war, in 1947, very shortly before I was born, there was a historic paper was published in the journal Nature by the German chemist Panev, who during Nazi times had moved to the UK and was working at the University of Durham. He laid down the ground rules which exist to this day for the naming of elements. Number one, the right to name an element should go to the first, presumably group or person, to give definite proof of the existence of one of its isotopes. Second point, in deciding the priority of the discovery, there should be no discrimination between naturally occurring and artificially produced isotopes. And the third point, and this is very important, if a claim to such a discovery has been accepted in the past but is refuted, that means contradicted, by later research, the name should be deleted and replaced by one chosen by the real discoverer. And those rules applied to this day. And it was technetium that really precipitated this. So what happened then was that the names of 6 new elements, including plutonium, were accepted, and Sigret and Perrier were invited to name their element, and they chose the name technetium in the same journal in a really short paper from the Greek word which means synthetic. So it is embodied in his name that it was the first synthetic element. In the early 1960s, with the improvement of instrumentation, people discovered that in uranium minerals, because of the radioactive decay of uranium, you can detect tiny, tiny traces of technetium. And therefore, it is natural after all. So the name isn't quite right. And then in 1972, there was an extraordinary discovery by geologists in Gabon in Africa, where they discovered that in a uranium deposit underground about 1 million years ago, a natural nuclear reactor had started. There was a high enough concentration of uranium for a nuclear reaction to take place. And because of this nuclear reaction, there were in fact traces of technetium found under the ground. Because of all the nuclear research that was done during the Manhattan Project, there was an abundant supply of technetium became available after the Second World War, and people started studying the chemistry. And you can get a wide range of compounds. And as you might expect, the chemistry is perhaps a little closer to rhenium than to manganese, because heavier elements tend to be more similar. But one of the most interesting applications turns out to be in medicine. The application is in diagnosis. When people have cancer, it's often quite hard to see the tumours, or particularly the secondary tumours that spread across somebody's body, because they're small and they are not easily imaged. But it turns out that if you take radioactive molybdenum 99, it decays by emission of electrons to make technetium. But very unusually, and something which we've never talked about before, the technetium is formed with the nucleus in an excited state, that is, with higher energy than it might have otherwise. And this excited state is symbolized by the letter M, which stands for metastable, which means it's stable for a short time but not very long. And so what happens is this metastable technetium decays to the stable isotope, or stable state, but with the same mass, and gives out a gamma ray which can penetrate a large distance through, for example, human flesh. And then much more slowly, the technetium-99 decays to ruthenium. So what happens is that if you do your chemistry very quickly, you can isolate this technetium-99M, and before it decays, you can react it with another chemical which will complex, that's bind round the technetium, and you choose this binding chemical so that it will also bind to tumour cells. Selectively, it will bind to the tumour and not to ordinary organs. So quickly you inject it into the